This is video 3 for week 8, and in the previous videos we kind of just reminded ourselves of where we are in the story of differentiability in multivariable calculus. And last video we introduced some nice notation, that gradient operator or the nabla symbol, and now we want to we really want to extend our understanding of differentiability, and we're going to first extend it to a scenario where we have n inputs. Okay, we're not talking about many outputs yet, but we're just talking about many inputs. Okay, so really we've seen one input in the case of single variable calculus. We've seen two inputs, which we dealt with last week, and now for n inputs, the story hasn't changed that much. Okay, we're just saying that now if we have n inputs, we still are thinking of that h of x function, which is kind of that locally tangent plane. And so now I have that gradient operator in there. That's how we define it. And so my question for you is, does that look any different from what we saw last week? If you look closely, I don't think so. Okay. So it's just looking at the difference between f and that locally linear the locally linear function, and then the difference in the distance between our vector x and the point or the vector a. Okay, we want to make sure that that limit is 0 eventually. Okay, so an example here, which we won't complete fully just for time purposes, is so I'm given an f, right? And so if I want to find, or if I want to prove that it's differentiable, right, that means, well, I need to show that this limit is 0, right? That was the condition that I was given. Okay, so if I can say that limit's 0, then I can say it's differentiable. Okay, so let's keep that on our screen. And, well, okay, right, I need to find h of x first. Okay, well, so step 1, find h of x. Okay, well, if we look back, that's actually going to be a little bit long of a process, right? So I need to find the point, or the function value at that point. So, okay, well, let's just go ahead and do this piece by piece. Okay, f of a, and then plus gradient of f at a dotted with x minus a. All right. F of a, I believe you can calculate this out. 4, and then plus the gradient of f. Well, okay, let's do some side work and figure out what that is. Okay, so the gradient of f here in this instance should just be, and I'm going to write this as a vector, it's going to be 2x, 2y, and then 1/2 z to the minus half. Okay, and then if I evaluate this at AB, I believe, oops, yep, that's right. I believe I get 2, 0, and 1/4. Okay, and it should actually be A, B, C. Okay, where this is A, B, and C. All right. So, okay, I found that. So then I can write this in as 2, 0, 1/4 dotted with, and then this is going to be x minus 1, I'm doing the subtraction of these two vectors right away, and then y, and then z minus 4. Okay, and just for my own purposes, if you're ever asked to find h of x in these scenarios, I actually really like it in this form. It's easy for me to grade, so try and leave it in this form without doing the dot product. Okay, but then if we end up reducing this, I would end up getting, and I should kind of maybe do my work a little bit differently. I believe I end up getting 1 plus 2x, and there is some simplification that I've done in the background, plus 1/4 z. Okay, so I found h of x, right? And then now step 2 would be really to show that the limit as x approaches this point that we have of f of vector x minus h of vector x over the magnitude or the distance between vector x and a is 0. Okay, and that can be a very long and tedious process, and I'm not going to do it in this video. I encourage you to work it out, and if you have questions, let's talk about it next time we meet for class. Alright, and that's going to kind of be the end of this video. In the next video, we will talk about what we're going to call the grand definition of differentiability and some things related to it. Alright?